Good morning. All right, we will start momentum today. But before we do that, one last little topic to cover for work and energy, and that's power. Power. We don't use it a lot in physics 4a, but you'll use it in physics 4b a lot, and in physics 4c. So I just want to make sure you understand what power is and why it's useful. Power is work over time, work divided by time. So it has units of joules per second. We get tired of writing joules per second all the time, so we write watts. Power is units of watts, a joule per second. The thing that power tells us is, let's say you have two cars that have the exact same mass. They're both at the metering light, waiting to get onto the freeway. The light turns green. They accelerate up. Both of the cars started from rest. Both of the cars eventually get up to freeway speed, but one car does it much faster than the other car. Both cars' engines were capable of doing the same amount of work, right? Getting the same mass car from rest to some kinetic energy. They both did the same amount of work, but one did it much faster than the other one. Is that important to you? Maybe it is. That's what power tells us. So both engines did the same amount of work. One did it faster. It's more powerful. Maybe you're lifting boxes off the floor, trying to get them up onto a platform. You have a motor, two motors, you're looking in catalogs, two motors can do that work. One can do it much faster than the other one. Maybe it's more expensive, and you have to decide, is it worth, if I'm just lifting a few boxes, I'll buy the cheaper one. I don't care how long it takes, right? If I'm lifting lots of boxes, I'll buy the more expensive one because it's going to get the job done much faster. You have to think about things like that. So that's where power comes in. Even if two engines can do the same amount of work, sometimes one can do it faster than the other one. That's useful information. Another unit you might see for power is horsepower. A lot of cars are rated in horsepower. A lot of motors are rated in horsepower. That's our non-SI unit for power. The SI unit is the watt. You can't see the screen. I'm not writing anything, but you should be able to see the power here. There we go. Okay. All right. So we discussed power, and that's about all I'm going to cover on power. But don't tell your 4B instructor you've never seen power before. You've seen it. We talked about it. And when you get to 4B, the reason we use it so much in 4B is because we have circuits. And in circuits, the charges are moving. We call that current. Energy comes from charge. If we talk about how much charge something has or uses, we can talk about the energy. But current is charge per unit time. So if we're talking about current, we're talking about charge per unit time, and then this light bulb can consume this much charge per unit time. It can consume this much energy per unit time, and this device can use this much energy per unit time. Everything is in time because our current is charge per unit time. Everything is per time. So to talk about energy would be not a very convenient way to talk about things, because as the current changes, the energy changes, but the power is much easier because it's energy per unit time. So if we're talking current, usually we talk power, not energy. How much power is this device consuming? How much power is that device consuming? And if we want to know the energy, then we say, well, how long was it on for? How long was that light bulb lit up for? Then we can figure out how much energy it consumed. But usually we think in terms of power. So it's important to at least understand. Okay. Looks like we have not the best connection. Sorry about that. Maybe it will stabilize as we move forward here. All right, so let's move into momentum. And we're going to go through a worksheet and try to get you a nice introduction to momentum, and we'll go over some of the sticking points that students have with momentum. So we've got these two situations here. We've got block A and block B, or cart A and cart B. They're initially at rest on a horizontal frictionless table. We're looking down from the top. A constant force, F0, is applied to each cart as they travel between the two marks on the table. Cart B has twice the mass of cart A. Let's see, is this, what can we do here? Let me see. Well, let me just try stop. I'm going to stop sharing my screen, and we'll just try to reconnect it. I'm not sure what else I can do here. Okay, I've just stopped screen sharing and restarted it. I don't know if that's going to do anything. My computer tells me my internet connection is strong, but Zoom tells me my internet connection is unstable. I don't know what that means. Maybe Zoom is having some issues. Okay, we'll continue, and let me know if there's still issues. I don't know. Maybe we log out and log back in. That's the next thing I can think of. Okay. This is our situation. We've got our two blocks, frictionless table. One is heavier than the other one, and we're exerting the exact same force on both of them the whole time they're traveling between these two lines. So the discussion here, 3 students discussing this issue. Since the same force is exerted on both carts, the cart with the smaller mass will move quickly, while the cart with the larger mass will move slowly. We agree with that? You exert the same force to 2 carts. One is more massive than the other one. The light one moves quickly or has greater acceleration, right? The heavier one moves more slowly or has less acceleration. The momentum of each cart is equal to the mass times the velocity. So we haven't introduced momentum yet, but we are right now. Momentum is mass times velocity. That is correct. I guess we're running out of, there's so many M's in physics, we're running out of things. We use P, lowercase p, for momentum. Mass times velocity. The units for momentum. Mass is kilograms. Velocity is meters per second. And for some reason, we never get tired of writing kilogram meters per second. You would think that there would be some other unit for that, right? A Galileo or something, I don't know, but there isn't. Kilogram meters per second for momentum. So student one here restates a lot of stuff, but doesn't really tell us anything, right? Since the same force is exerted on both carts, the cart with a smaller mass moves quickly. Yes, we agree. Since and the larger one moves more slowly. Yes, and the momentum is mass times velocity. Yes, that's the definition of momentum. So that's all true, doesn't really tell us very much, right? Let's move on to student two. This must mean that the speed compensates for the mass and the two carts have equal final momenta. So they're agreeing that the heavier cart is moving more slowly, but they're saying that since momentum is mass times velocity, the bigger cart has more mass, the lighter cart has more velocity. When you multiply them together, you get the same thing. What do you think? Maybe. Maybe, I don't know. That's possible. Very possible, but not necessarily, doesn't necessarily have to happen that way, right? And student three says, I was thinking about kinetic energy. Do you agree with them? Were they really thinking about kinetic energy? Since the velocity is squared in kinetic energy, but the mass isn't, the cart with the bigger speed will have more kinetic energy. Okay, so again, stating some stuff that we know. Kinetic energy is mass times velocity squared. So the first student two says momentum is mass times velocity. I know one of these carts is moving faster than the other one. Maybe that compensates, and when I multiply mass and velocity together, the momenta are the same. Student three says kinetic energy is mass times v squared. And so V is going to have a much bigger effect. So they're going with the, what are they going with? The lighter one, right? They're saying the lighter one that has the bigger speed, since speed is squared, that has the bigger effect, they're going to end up with more kinetic energy than the heavy cart. Possibly, right? Possibly. It's logical, but we don't know for sure if it exactly compensates that way. All right, so good stuff to think about. Let's see if we can figure it out. So we'll go through these kind of one at a time. Which cart takes longer to travel between the two marks? The heavier one, yeah. Cart B. Oops, where did I put that? Wrong place. I can fix that. There we go. Says use Newton's second law and the definition of acceleration to derive an equation for each cart relating the net force to the change in velocity and the time. So what they're asking for here is, I think I'll just do it, save a little time. But they want us to start with F equals ma. So sum of the forces equals ma. And we know that a is the change in velocity over time, right? So using that, I can get this, sum of the forces is m times delta v over delta t. I'm running out of room here. So there we've done it. We've got the sum of the forces is the mass times the change in velocity over the change in time. So they're asking, is the quantity m delta v for cart A greater than, less than, or equal to m delta v for cart B? Can we figure that out? We're trying to compare this quantity, the mass times the change in velocity between these initial state and the final state, is equal to the force times the time interval. And what do we know about the force? It's the same. And what do we know about the time interval? It's not the same, right? One of these took a lot longer to get to the other side than the other cart did. That's an A. I guess I should leave the deltas there. Okay, that brings us to our next equation, impulse. The net force times the time is equal to the mass times the change in velocity. This is the impulse. This is the change in momentum, delta P. Impulse is equal to change in momentum. So that's where we start off on the next page. It says for a constant net force, F times delta T is called the impulse imparted to the object. Impulse is a vector quantity. Momentum is a vector. Change in momentum is a vector. Impulse is a vector. Where does impulse get its direction from? The net force. Time is a scalar. Time doesn't have direction associated with it. So the direction comes from the net force. So the net force equals, where does momentum get its direction from? Velocity. Momentum gets its direction from velocity. Mass is a scalar. And so delta P gets its direction from delta V. So you're starting to link things together. What is going to give delta V its direction? The net force, right? Net force is going to tell us the direction of the momentum change or the change in velocity. So what does number 2 here say? It says, let me add one more thing here. I want to make a correlation to what we just learned. We've got momentum, we've got impulse. Impulse, I think our book uses I for impulse. Some books use J, some use I. Capital I is the impulse. Force times delta T, mass times velocity. I'll just write them all out like that in a row. Momentum, mv. And then last time, we were working with the work kinetic energy theorem, right? With the work and energy. Work is change in kinetic energy. Well, now we have the impulse momentum theorem. And that is that the impulse is equal to the change in momentum. And they are very similar. Oftentimes you can use one or the other one to get to the same result. We'll go through some examples. Okay, let's continue with our worksheet. Is the magnitude of the impulse imparted to cart A greater than, less than, or equal to the magnitude of the impulse imparted to B? Which one of these is bigger? B is the heavier cart. It takes longer to get to the other side. Both of them had the same force acting on them. The one that had the force acting on it for a longer period of time has the greater impulse. B is greater than A. Okay. Now it says, what does it say? Write an equation showing how the impulse imparted to A is related to the change in momentum Okay, I think we've got that already, right? Impulse equals change in momentum. This is the impulse momentum theorem. Okay, we've got that right there. Is the magnitude of the final momentum of cart A greater than, less than, or equal to the final momentum of cart? So now we're trying to answer the question that one of the students proposed earlier. Which cart has more momentum at the end? B, because it had a great, they both started at 0, right? If we have to know, the only thing impulse momentum tells us is the change in momentum. Because B had a bigger change in momentum and they both started at the same 0, then B has to have a final momentum that's greater. So we're answering some of these questions. But student B, what was it? Student 2. Student 2 said, this must mean that the speed compensates for the mass and the two have equal final momentum. So student 2 thought, momentum is mass times velocity. One of them has a bigger mass, smaller velocity. The other one has a smaller mass, bigger velocity. By the time you multiply them together, you're going to end up with the same thing. It turns out that's not the case. We just saw that's not the case. When you multiply them together, it doesn't compensate. The momentum of B is more because the time interval was very important, right? The time interval. Now it says student 3 was talking about kinetic energy. So now we want to start thinking about kinetic energy. Let's see what happened there. Part D, it says, how does the work done on the cart A, compare to the work done on cart B? Work done on cart A, work done on B, how do they compare? They are the same because work is force times distance. They both had the same force applied to them through the same distance. The same amount of work was done to both carts. Is the kinetic energy of cart A greater than, less than, or equal to the kinetic energy of cart B at the end? There we go. Work is equal to the change in kinetic energy. So they both have the same change in kinetic energy. They both started with the same amount, 0. So they both have to end with the same amount. Right. Now it says go back and check what the students said again. So we are doing that. Student 1, we were okay with what they said. They kind of just restated a lot of facts, didn't really give us much. Student 2 is wrong. The momentum of B is greater than the momentum of A at the end. And student 3 was also wrong. Student 3 said that the kinetic energy would be more for the lighter one because it was going faster, v squared, so the velocity has the bigger effect. But it turns out that that's when it compensates exactly. All right. What we're going to find, I'll just give you a little preview. What we're going to find is that momentum and energy can be used sort of in similar cases. But the key is that there are going to be instances where we can't use energy and we think, oh, how are we going to solve this problem? We can't use energy, but we can use momentum in those cases. So even if energy is not conserved, and of course by that I mean mechanical energy, right? Sometimes, like for example, during a collision, some of the mechanical energy, things like kinetic energy and gravitational potential energy and spring potential energy, that's mechanical energy. Some of that is converted into sound. Some of that is converted into thermal energy. Surfaces heat up when they collide together. Some of that goes into deformation, bending metal. If you bend a piece of metal and it doesn't bend back, you've used up some energy to bend that metal, to change the chemical bonds in the metal, the structure of the metal. So the mechanical energy can get converted into other types that we can't account for. That's what I mean by not conserved. Of course, if we could account for all of those, we would be able to solve the problem. But even if that's the case, even if energy is going into deformation and sound and heat, we can still use momentum to solve a collision problem under most circumstances. Okay, so here we have two gliders on a frictionless track. In the first case, cart A is coming in and there's a heavy cart M at rest, and cart A collides with it and bounces back, and M slides off to the right. And in the second case, A comes in, hits it, and comes to rest, and the other one slides off to the right. So it says, what differences between M and N could account for the different behavior of the collision? So in one case, you've got a cart at rest. Another one comes in, hits it, and bounces back. And then this one goes off. So it bounces back like this. And the other case, it comes in and just hits it and comes to rest. And this one comes out. I think the masses are all the same here. Yeah, so there's some kind of how, I don't know what we should call it, how elastic the surfaces are. You can certainly think about designing a ball that's a hard rubber ball that is really bouncy, and taking another ball that's the same mass but maybe it's designed a little differently where when it hits a surface, it doesn't really bounce very well. It just kind of hits, and maybe the rubber is loose and there's some air pockets in there or something. So same mass, but when it hits a surface, it doesn't have that same bounciness as the hard rubber ball would have. See what I mean? So you can make one surface more elastic, I guess we could say, but more bouncy. I'm okay with that. I'll just say different materials. Now we want to draw a free body diagram for block A. At some point, it says draw and label a free body diagram for A and M at an instant during the collision while the two are in contact with each other. Free body diagram for A, free body diagram for M, at some instant while they are in contact with each other, during that collision while they're in contact with each other. Okay, I'll do the easy ones. Those are the vertical forces, right? How about the horizontal forces? Anything acting on A horizontally. A force to the left, when it hits M, M pushes back to the left. So there's a force here. M on A, that's an M. And on the other one, there's a force to the right, A on M. This is an M. Let me try to. Okay, good. When they collide, A pushes M this way, M pushes A that way, and those forces have to be equal and opposite because it's a Newton's pair. It's a single interaction. Anytime two objects exert forces on each other, they are equal and opposite. And it doesn't matter at what time we draw this diagram. Maybe as those blocks come together, the instant they just touch, there's a tiny force on M in that direction. There's a tiny force on A in that direction. And but they're equal and opposite. An instant later, the two surfaces are kind of sinking into each other a little bit. Now there's a big force in this direction on M, and there's a big force in that direction on A, but they're still equal and opposite. And now they start to come apart. The two blocks are moving in opposite directions. They start to come apart. The forces become small again. A is only pushing with a small force on M. M is only pushing with a small force on A, but they're always equal and opposite as they come apart. The entire time they are in contact with each other, there's a single interaction taking place there. Those forces are always equal and opposite. So to answer this question here, F net on glider A is always equal and opposite F net on M. Okay. I think we answered that. Now they're asking us to consider a time interval while the gliders are still in contact with each other. So it says, how does F net times delta t compare for the two blocks? F net for A, we just care about the magnitude here, times the time interval for A. How does that compare to F net M times the time interval for M? Right, so think about this. If these two blocks are push into each other and then push apart, and it takes some small amount of time, pick a number, I don't know, 0.1 seconds. If A is pushing on M for 0.1 seconds, then M is also pushing on A for 0.1 seconds, right? The times can't be different. It's the two of them are touching each other the whole time. So the delta T's have to be the same. Here, I'll put it. And we said the force is the same. So these are equal. So I could write it as, does it ask me to do it somewhere? We could write it this way, right? We could write it as the impulse on A is equal and opposite to the impulse on M, if we wanted to. Right, time of contact. Okay, so it says, draw and label vectors to represent the initial momentum, the final momentum, and the change in momentum of A in each case. So the first case, it bounces back. Is that right? Got to remind myself here. Yeah, in experiment 1, A comes in, hits M, and bounces back in the opposite direction. In experiment 2, it comes in, same mass, same velocity, hits N, and comes to rest. So it's trying to get us to figure out which one had the greater change in momentum. We're going to start with vector addition. Vector addition. So the change in momentum is final minus initial. And these are vectors, so I can do the vector addition. So for experiment 1, the initial, well, there's not a lot of room here, is there? P initial looks something like that. P final looks something like this. So delta P is P final minus P initial, right? P final is this one. P initial, the opposite of P initial is this one. And so what is my delta P? It's this vector right here. Did you follow? For experiment 2, P initial is the exact same. Both times the cart comes in with the exact same momentum. But the final, what's the final? 0. It comes to rest. So my final, where am I gonna draw it? How about right here? Minus P initial is this. Okay, so which one? We okay with that? It says, how does the change in momentum of M compare to the change in momentum of N? Well, how about A? Let's just look at A here. I don't think I finished question 1 here. The magnitude of the change in momentum of glider A, we want to know. We want to know the change in momentum of A. In case 1, how does that compare to the change in momentum of A in case 2? Much greater. This one, A had a change in momentum that's smaller than in this case, right? This one over here, much bigger. So the change in momentum for we're only looking at block A now. Block A comes in with the same momentum in both cases. One case, it bounces back. So because momentum is a vector quantity, that's a huge change. It went from positive to negative. That's a really big change. Whereas going from something to 0 is not as much of a change. It's like half as much, right? That's the point here. Okay, so if A had a bigger change in momentum in the first experiment with M than it did with N, then what do we know? How can we compare M and N? Which one has a bigger change in momentum, M or N? We have to kind of look back up to what we had earlier. let's just think about one collision. Earlier we said impulse on A equals the opposite of the impulse on M. So if A, what is impulse? Change in momentum. If A has a small change in momentum, M has a small change in momentum in the other direction. If A has a big change in momentum, M has a big change in momentum in the other direction. Because the force that A is changing A's momentum comes from M, right? That comes from that interaction. Okay, so real quick, let's finish this one page here. If A has a greater change in momentum in case 1, in experiment 1, and we know A and M will have the same impulse, the same change in momentum, but opposite direction, and A and N in case 2 both have to have the same change in momentum, right? So then M has to be greater than N. Delta P, change in momentum for M, has to be greater than change in momentum of the other one. And which has the greater speed? They both have the same mass. So the velocity of M greater than the velocity of N. And I think you'll see that the statement isn't quite right, but we've talked about it. M, when two objects collide and interact, the change in momentum of one equal and opposite to the change in momentum of the other one, because the forces that they're exerting on each other are equal and opposite, and the time interval that they're interacting with is the same. So they always have equal and opposite change in momentum. Okay. All right, this is a good stopping point. 10-minute break. I'll pause the video. Question here about whether the mass matters. These two carts, A and M, have different masses. It does not matter. Because this all comes from impulse, right? Force times the time interval. Impulse is change in momentum. When two objects interact with each other, the forces have to be equal and opposite. The time has to be the same. So the impulse, the change in momentum of cart A has to be equal and opposite to the change in momentum of cart M. Doesn't matter which one's bigger, which one's going faster, none of that matters. Because they interact for the same amount of time and the force is equal and opposite, the impulse has to be equal and opposite. The change in momentum has to be equal and opposite. Okay, good. So there are a lot of subtleties in here. Maybe some of it seems obvious now. Maybe some of it seems like it's coming from someplace new. We're going kind of fast. You haven't seen it before. I don't know which end of the spectrum you're on, but it might pay to go back. Either way, it might pay to go back and look at some of this after we've done momentum for a couple of days, because some of this you're going to forget. You know, trust me, if I ask you a week from now, if two objects collide and the momenta are equal and opposite, you're might not get it right. So that's one of those little subtleties that should always be true. You should be go back and review that. And then we want to get into one of the problems that it's like anything, energy conservation. Well, it's easy to say energy is conserved, but well, there's a lot of reasons why mechanical energy would not be conserved. Friction in the system, external work being done, things like that, right? The mechanical energy might be converted into other kinds or transformed into other types of energy. Well, similarly with momentum, if your system has to be defined properly to have momentum conserved. And so we want to get into that. When is momentum conserved? When can we say momentum is conserved and when isn't it? Okay, we've got two gliders on a frictionless track. Glider C sliding towards D. And it says D is free to move. C rebounds. That means it bounces backwards after the collision. In the space provided, so this is the initial here, this is the initial, and the final would look like this is initial. Okay. We want to draw free body diagrams for C and D and the system, which is both carts together. Free body diagram. This is at some point during the collision, while C and D are in contact with each other. Free body diagram for C, free body diagram for D, and a free body diagram for the system. Okay, I did all the vertical ones for you. So we've already done one of these, right? When C collides with D, D pushes back on C. So we're going to get a force in this direction. What are we calling that? We could call it a normal force. I didn't call it. I just called it an F a force last time, but whatever you want to call it. There's a force here. Normal force, a force. How about for the system? If we're drawing a free body diagram for the system, do we include those forces? Right. Internal forces are not shown. We just care about external forces when we draw these free body diagrams. Okay, so it says the momentum of a system containing multiple objects can be defined to be the sum of the momentum of each of the parts. So what that says is we can add up the momentum of A and the momentum of B, and we get the momentum of the system, A plus B. Right, so the momentum of the system is the momentum of C plus the momentum of D. So how about the change in momentum of the system? Oops. Hate when that happens. Okay. Okay. So the change in momentum of the system would be the change in momentum of C plus the change in momentum of D. We okay with that? You see where I'm going with this? C and D are colliding with each other. The change in momentum of the C is, how does that compare to D? Equal and opposite. Yes. Equal and opposite. Let me write that here in red. So that means the change in momentum of the system is 0. So we would say momentum is conserved. It does not change throughout this process. When C and D collide together, C's momentum changes, D's momentum changes, but the momentum of the system stays the same, does not change. The delta P for the system is 0. So whatever momentum it had before the collision, it has to have the same amount after the collision. And we can use that even if the mechanical energy is different before the collision and after the collision. We can still use this new law that we're learning, conservation of momentum. We could still use this. So we're trying to get a grasp for when we can use it and when we can't. Glider C, it says, is the momentum of glider C, does it change during the collision? Yes, right? The glider C comes in one direction, how is it? Comes in, hits, and moves back, right? So the direction changed. So it had to have its momentum as a vector quantity. So therefore it changed, right? How about D? Yes, D was sitting there at rest. It got whacked by the other cart, and then it was moving. So it went from 0 to something. So its momentum changed. And the system? No, we just answered it right there, right? Now I want to think about the net force on each of these, or are we going to come back to that later? So is there a net force on C? During the collision? Yes. Where's our free body diagram? Yeah, we have this There's a net force on C, and that net force has to be in the same direction as the change in momentum of block C. Is there a net force on D? Yes, there is, and that has to be in the direction of the change in momentum of D. Is there a net force on the system? No. There's no net force on the system. All right, so we're going to keep going here. We're going to one more case of these two blocks interacting, and we're going to try to figure out when is momentum conserved, when can we use conservation of momentum. So now we're going to do this again. We've got C coming in, but this time D is not free to move. D is fixed in place. There's a pin going in here holding it, locking it to the track. There's a pin there holding it to the track. It's fixed in place. Okay. D cannot move. All right, so C comes along, hits D, bounces back, and you're going to draw free body diagrams for C, D in the system. So C looks the same. D has another force now, right? From the pin that keeps it in place so it doesn't move. And their system now has a force acting on it, right? Okay, we okay? Let's see. Does the momentum of C change during this collision? Yes. How about D? No. It's sitting there at rest before, it's sitting there at rest afterwards, it does not change. How about the system's momentum? Yes, because the system is C plus D together. So the system had the momentum of c initially, and at the end, the system has the momentum of c because d doesn't have momentum in either case. So systems changed. How about the net force on C? It is not zero, right? There's a net force acting on C. The net force on D is zero. And the net force on the system not zero. So if we look over these cases, the system would be moving, right? Because C is moving. The system has net motion because C is moving. Okay. This is the conclusion here, the big conclusion. We're about to get to it. When yeah, I think we were talking changes in momentum, right? Not momentum, changes in momentum. The system may have had momentum in the previous case. Where's the previous case? Here. The system has momentum at the beginning and it has momentum at the end, but it didn't change. The momentum didn't change during the collision. Because this has momentum, the system's momentum initial is not zero. But what we found here is that the change in momentum of the system had to be zero. So that means the momentum is the same at the end. Whatever it had at the beginning, it has at the end. In the previous case or in our new case here, with the pin in it or not? In this case, there's no net force on the system because it's a frictionless track and nothing's holding those blocks in place. The only horizontal forces are within the system, C to D, D to C. Those are the only horizontal forces in our system. You see that? And they come from within the system. There's nothing external. But in this case, the system does have something that's reaching in so that the two internal forces don't show up when we draw our free body diagram for the system. All we care about are external forces, but we do have an external force acting on our system here. So external forces. It says, when momentum of an object or system did not change, were external forces on the system? Up here, if we only did the first experiment, we had two cases where it did not change. Both times the net force was zero, right? but we don't care about net force. We care about external forces. These were all internal forces. So let's come down here. Let's look at this one. So this has external force acting on it. The system has an external force acting on it. The glider D, momentum did not change. For the system, momentum did change. So does an external force matter? We found cases for both. I would say yes and no. But I think if we look at all these cases, it will be very consistent when the net force is non-zero. Let me see, how did I do this? Oh, no means no means the momentum stays the same, right? No change in momentum. Net force is 0. No change in momentum. Net force is 0. So for this one, when the momentum did not change, no, there was no net force on the system. Every time. It's 2 words. So the net force is what we're gonna link, not an external force, a net force is what's important. Let me write that here somewhere. I'll show you why. Sum of the forces equals ma. What is A? dv dt. So we're going to plug that in there. What do we get? We get sum of the forces is m dv dt. Okay, so far so good. This is all stuff we know. Newton's second law and the definition of acceleration, right? That's all we're using so far. So we're going to move the mass inside. If the mass is constant, we can bring it inside, right? If constant, we can write it this way. What is m times v? It's momentum. This is how Newton came up with this idea. He saw this equation. He said, wait a minute. The derivative of this special quantity, m times v, with respect to time, has to be 0 when there's no net force, when the sum of the forces is 0. The derivative has to be 0, or m times v has to be constant in time, right? The derivative has to be 0. Wow, there's something special about this quantity, m times v, that it cannot change if there's no net force acting on the system. It cannot change. And that, we'll give it a special name. We'll call it momentum. Actually, this is the way Newton wrote Newton's second law. We write Newton's second law, sum of the forces equals ma. But that actually is for the mass being constant. Newton didn't write it that way. Newton wrote sum of the forces equals dp dt. And that works even if the mass is not constant. Sorry, which one are we talking about now? The net force on the object or the system. So for C, let's just look at each one. For C, while C and D are interacting, we've got a force in this direction, but nothing in the other direction, right? So there's obviously a net force acting on C at that during that time interval. We okay with that? For D, while C and D are interacting, D doesn't move. So we know this force and this force are equal and opposite, but D is held in place. So that means that this force, there's some outside force pushing on D, keeping it from moving. D doesn't move, right? Sum of the forces equals ma. The acceleration is 0. D never moves. It stays in the same place the whole time. So the net force on D had to have been 0. And the system has a net force acting on it, yes. So C has a net force. The system has a net force. D does not. It's not 0. I said it's not 0. Is that what I said? Not 0 means there is a force. Good. Oh, I said, what I said was when momentum does not change, when the momentum does not change, so let's go back and look at when the momentum does not change. Here, the momentum does not change. There's a net force of 0. Here, the momentum does change. There is a net force. Here, the momentum does change. There is a net force. So I just went through and looked at all the cases where I had no change. every time I had a no here, no change, there was a zero force. That's what I meant by this. Okay. It's a little wordy, I know. But I think this, maybe I should have started with this. I don't know. It's we all know F equals ma. We know it. We love it. We use that equation, right? F equals ma. We know the definition of acceleration, dv dt. We plug that in, and we immediately get sum of the forces equals the change in momentum with respect to time. And so that special quantity m times v is constant when the net force is zero. So this equation tells us a lot. So I have a ball, I drop or something, I have something, I drop it. It had no momentum. I let go of it, had no momentum. It starts to move. It gets more and more momentum. The split second before it hits the ground, it has lots of momentum. It hits the ground, has zero momentum again. Students often ask me, what's going on? How can I use momentum conservation? It had no momentum, it had momentum, it's back to zero again. Because you have to look at your system. You have to define your system. Why? Because there cannot be a net force acting on the system. This has to be zero to use momentum conservation. So if my system is just my object, my ball, whatever it is, and I let go of it, is there a net force acting on it? Yeah, gravity. There's a net force acting on it. So how do I get rid of the net force? I have to include the Earth in my system. If I include the Earth in my system, then the Earth pulls on the ball and the ball pulls on the Earth. Those internal forces cancel out. Now I have no net force acting. I can use momentum conservation. And the same with the collision of the ball hitting the ground. Actually, the same any point in there, any point in between. And the collision, the ball has momentum right before it hits the ground, and then it goes to zero. But if the Earth is part of our system, technically we could use momentum conservation then. If the Earth's not part of your system, you have a net force. You have some net force acting on the object, causing it to stop moving when it hits the ground. Okay. Let's see. How about we do we do this. A constant force is exerted to a cart that's initially at rest on a frictionless track. The force acts for a short time interval and gives the cart a final speed. To reach the same final speed using a force that's half as big, it must be exerted for a time interval that is how much? 4 times as long, twice as long, half as long? I should set up a poll, shouldn't I? Force F acts for a certain time interval to get that cart to a final speed. We want twice the force to get it to the same final speed. We use what time interval? Or sorry, half the force. We would use what time interval? Okay. So basically we've got F1 T1 has to equal F2 T2 twice as long, right? Impulse momentum. Two carts, A and B, on frictionless tracks initially at rest. A is twice as massive as B. Now you exert the same force on both carts for 1 second. After that 1 second, the momentum of cart A is twice as much, half as much, the same. What is the change in momentum? Force times time. They both had the same force exerted on them for the same amount of time. So they both had to have the same change in momentum. They both started with the same amount. So they both end up with the same amount. All right. Two identical carts, A and B. They're initially moving now. A is twice as fast as B. You exert the same force for the same time. At the end of that time, the change in momentum of A is, how does it change in momentum compare? Okay, good. Almost everybody said it is non-zero and equal to the change in momentum of the other. Now the final momenta are going to be different because they started different. They started at different places. They both had the same change, but at the end, they're going to be different. They started different, they ended different, but they both had the same change. So the change in momentum is force times time, same for both. All right. Impulse momentum. So we see a lot, we see this all around us. This is one of those things that you almost can't avoid it. We see it everywhere. Impulse momentum. Car crashes. Why do we have airbags in our cars, crumple zones in our cars? Why did we see these barriers on the freeway that are filled with sand or water? It's all impulse momentum. So you're driving down the freeway, you've got a certain amount of momentum, right? Nothing we can do about that. You've got a certain amount of momentum. Your car crashes into a concrete pillar that's holding up an overpass, and your momentum comes to zero. Nothing we can do about that. Initial momentum, some fixed value. Final momentum, zero. Nothing we can do about that. But there are different ways that we can bring you to that final momentum. What is change in momentum? It's force times time. So one way we can achieve that change in momentum is just allow your car to crash into the concrete pillar. In the old days, cars were very rigid and stiff. They thought that was the way to make cars, big, stiff, rigid frames. So your car hits that pillar, what happens? The time interval is very, very short. It doesn't interact with the pillar for very long. Time interval is small. So the force has to be big, right? I'm drawing a pictorial representation of a big force acting for a small time. Or we can try to spread out the time interval. We can put a bunch of sand-filled buckets there. Your car has to plow through 3 buckets before it gets to the wall. Then when your car hits the wall, the front end collapses, and it takes a little bit of time. And then an airbag goes off, and your face hits the airbag, your chest hits the airbag, and that takes another few thousandths of a second out. And all of those things added up, we've spread out the time. So the time is big now, which means the average force acting on you can be small, right? 2 ways to achieve the same change in momentum. So all this stuff, the dashboard on your car probably has some padding in it. Well, maybe not nowadays with airbags, but that was what they started with. They started with putting padding in the dashboard of the car so that if your head hit that, there would be a little bit of give to it. Now we've got airbags and seat belts with tensioners and things like that. The crumple zones, all of this stuff helps spread out the time interval so that the same change in momentum can be achieved with a smaller average force. And this applies to so many things. We've got the cushioned running shoes. So you can, when you go for a run, those cushioning in the shoe spreads out the time interval that your heel is interacting with the ground, and that makes it a smaller average force acting on your bones, and it's a little easier on your joints and bones. If I asked you if you were running and you fell down and landed on a concrete sidewalk, or you were in the gym running on the basketball court in the gym and you fell down, which would hurt more? You'd say the sidewalk, because the gym, you might use terms like the gym floor gives a little bit. That's probably what you'd say, or it has some flex to it, it gives a little bit. That tiny amount, you might not think it's much, but think about the time interval that these collisions are taking place. The time intervals are very short. So if you can spread them out by 1/10 of a second, you might be able to cut your force by 20% or something like that, or 50%. Think about the time intervals. cases for your iPhone or your cell phones. So you have a cell phone, no case, you drop it, it hits the ground, and the time interval that it's interacting with the ground is very short. So the average force on the cell phone has to be big because your cell phone had a certain amount of momentum before it got to the ground, and it's coming to rest, right? It's coming to zero. No choice there. But you put that case on there, and even though the case doesn't look very big, they're specially made corners in those things that absorb that impact, and it spreads out the time interval. So it goes from a tiny, tiny amount to just a little bit longer, but that's enough to make a big percentage change in the force. Maybe the force is half or a third as much as it would be if the phone just hit the ground directly. And that's enough to save the phone a lot of times. So those cases are really good. And then my last example here, bungee jumping. You jump off that bridge, your body has a lot of momentum. At some point, you have a lot of momentum. And at some later point, you're going to have zero momentum, right? One way or another, you're going to end up with zero momentum. If you're attached to a bungee cord, we spread out that time interval from when you have maximum momentum to when you have zero momentum. And it takes place over a long period of time as that bungee cord stretches and stretches and stretches. And you can stop all that momentum you had comes to rest, comes to zero with a very small average force acting on you. Okay? Impulse momentum. We see it all around us. All right, I'm going to stop the video and I'll stick around and answer some questions.